Next up on our list of functional group-based chapters are the amines. After this, we're going to walk into some biochemistry, so this is the last of the functional group-based chapters that we're going to deal with in this course. So let's make it count. Happens to be one of the most important. So first of all, a few terminology differences from the past. Obviously, you know ammonia from general chemistry, and we've talked a little bit about different amines as we've gone along, but we have to clear up one thing. When we talk about primary, secondary, and tertiary, for the amines, we're talking about the nitrogen. So this is a secondary nitrogen. This is a tertiary nitrogen. We don't have to do that with alcohols or other functional groups, really, because they can't have multiple different substituents. So I don't have to describe an alcohol as the oxygen on an alcohol as primary, secondary, or tertiary. It's always the same. That's different here. So we have a little bit of a problem with that occasionally. Just be careful with it. For instance, we sometimes will say this is a secondary alcohol. Yes, this technically is a primary amine. Why? Because by default, we're not talking about the carbon. This is a secondary carbon, so is this. When we're talking about amines, we're actually talking about the nitrogen. So it's a little bit confusing. Just be careful which atom you're talking about, and really it only comes up in the amines. Otherwise, we're talking about the carbons all the time. So just be careful in this particular context. All right, amines in nature, everywhere, literally everywhere. Interesting that the example your book chose are all addictive substances, but we won't go there. Morphine on the left, cocaine in the middle, and nicotine on the right. Obviously, there are other functional groups here. We have ethers and alcohols in morphine. We have two different esters in cocaine, and we have an aromatic ring in nicotine. But the point is, the amine is generally the part where we have interactions biochemically. So we kind of have to pay a lot of attention to that. We'll talk more about that in the next set of lectures after this chapter. All right, in terms of neurotransmitters, this is an incomplete list. Adrenaline, noradrenaline, dopamine, three of the major ones, all derived basically from dopamine, but these are using kind of the wrong terms. These are more properly referred to as epinephrine and norepinephrine. And the other big piece of the puzzle, which they're not drawing here, is this one. Which is serotonin. So basically here is all of your mood regulation on one slide. Dopamine regulates not only motor skills and emotions, it's also motivational. So a deficiency in that tends to cause apathy, or what's called anhedonia, meaning not enjoying anything. It regulates your, not just, it's sometimes called a pleasure hormone, but it's really the one that regulates your anticipation of that. So it's kind of misnamed in that respect. Serotonin at the bottom tends to be more of your happy, and then with a little bit of derivation, it becomes melatonin, which regulates your sleep, whereas your fight or flight, fight, flight, or freeze, actually, there should be a third one there, are controlled by the other two, as well as things like your blood pressure, heart rate. The idea is that the amine is the central part here. When we look at drugs that act on these systems, basically the amine part is largely untouched, and we're dealing with only modifications elsewhere. So if we look at something like methamphetamine, which is acting on the dopamine system, it looks like this. We're looking at, it does not have the alcohols here, but the amphetamine has this, and if it's methamphetamine, one of the actual hydrogens is replaced. But basically, this piece, this phenethylamine, is still there, intact. And that's going to be true for a lot of other things. So when we look at having to deal with drugs, pharmaceuticals specifically, that are mimicking biological molecules, quite often we're going to have to leave the functional groups mostly where they are, and that seems to be more true of amines than of certain other functional groups. Okay, a few basics. We've dealt with some of this before, but not really in the context of the functional group itself. We can use nitrogens as nucleophiles or as bases. We've primarily talked about them in the past as bases, beginning with ammonia in general chemistry, looking at them as add-ons to other acid-base reactions that we've dealt with up to this point in 2 courses. We just kind of put amines in as a mild base to mop up leftover HCl, what you're seeing on the left here. But we do have to consider that nitrogen is also not just willing to donate electrons to a hydrogen, it's also willing to donate it to a carbon. That presents some benefits and some challenges that we're going to talk about when we get to making amines in the next video. A few basics on naming things. We generally name amines with the amine suffix if we can, and that is, so we're using an alkyl group as the prefix here. So kind of what we did with alcohols, so ethyl alcohol, isopropyl alcohol. We don't have a two-letter suffix here that works like ethanol and isopropanol. We use the word amine for that, so we don't use quite the same tricks we do with naming alcohols. But if we have something that's too complicated, then we may choose to call the amine a group rather than considering it part of the chain itself, so it becomes an amino group. So here are examples of that. Just to finish off the neurotransmitter bit from last time, if this were a carboxylic acid instead, that's GABA. That's gamma aminobutyric acid. So again, amines play a massive role in biochemical signaling. But again, we're just looking at the naming part for the moment. We'll talk about the biochemical aspects later. When we're talking about aminobenzene, that has a name, aniline. And so we tend to use that as a base if we're going to just functionalize it. We don't come upon this all that often in our context, but it's good to know. We talked about it a little bit when we did the aromatics chapter ages ago, but it hasn't. It's still a base name, just like phenol or anisole, where we can kind of keep certain functional groups as part of the main name and not have to number them, whatever. The assumption is that that's carbon 1. So here this would be metachloroaniline or 3-chloroaniline. Here, this is carbon 1. If it's part of the name, you're assuming that is carbon 1. So you want lower numbers, so 2 and then around to 4 instead of 3 and 5. 2 and around to 5 instead of 3 and 5. Sorry, I can count, just not today. Okay, multiple. We're just naming multiple alkyl groups. So if I have more than one, then I name them and alphabetize them just as we did back in intro in organic 1. Ethyl, methyl, isopropyl. Ethyl, methyl, propyl, sorry, not isopropyl. If we have more than one, di, tri prefixes are okay. Now, in terms of properties, before we head into actually making amines, we need a couple of things in our brain. One, this is approximately tetrahedral. It is not perfectly so because, as you might remember from intro and general chemistry, a lone pair takes up a little extra space. So this is kind of not being held on each side the way that a bonding orbital would be. So it flops around a little bit is the best way to think about it. So it pushes everybody else a little further away. So this is a little bit smaller of an angle than 109. They're saying 108. I've seen 107 more commonly, but the idea is it's compressed down slightly. Does it make a big difference to us? No, not in terms of reactivity. You're not gonna say yes or no to a reaction based on a 1 degree angle change. It's not that kind of it's not that strict. Most reactions are not anywhere near that intolerant of slight changes. So a few things about properties before we go any further. I'm not really going to beat you up over boiling points, but there's something here worth talking about, and it's these last two. So same carbon structure, a difference being an amine and an alcohol. So you would think that the amine, having more hydrogens to work with, would have a better layout of hydrogen bonding, which is the intermolecular force going on here, and therefore would have a higher boiling point. It does not. Why not? The answer, because its electronegativity is lower. So its hydrogen bonds are much weaker. They do exist, hence the difference between here and here, It's considerable, but they're not drastically strong to give you the type of boiling point changes that we see for things like alcohols, and in the extreme case, something like water. So keep that in mind. Hydrogen bonding is there, but it is not as energetically important as it is in alcohols. Okay, I left this slide in because I thought it was funny. Demented sense of humor, plus I've handled one of these before, so I can directly speak to it. Yes, amines smell bad, okay? Rotting fish is not the term I would use for something that has the word cadaver in it, okay? This is the smell of dead human. So, the rotting fish is not the term I would have used there. I don't know exactly why that's one of the things that forms, but it is a very, very distinctive smell, and one that basically you don't want to encounter. Even in a laboratory setting, it is atrociously unpleasant. So unpleasant here is a very mild term. Keep that in mind. All right. Basicity, if you remember back to what we talked about with ammonia in general chemistry, we do have a base. That lone pair can be donated to pick up a hydrogen, so we're talking about a Bronsted-Lowry definition of a base. It also works as a Lewis base if it were just an electron donor to a metal. We don't really need that right now, but it's still an issue. What we get is a much weaker acid, and so therefore this equilibrium lies to the right. If you remember talking about acid-base equilibria back in the day, the way that you could compare them was looking at these pKa values and saying, all right, the one with the lower pKa value is going to tend to be the one that gets rid of a hydrogen, which means the reaction goes away from that towards the other side, and that's what's implied here. So we're going to come back to that in a couple of different contexts in this chapter, because it's going to have some relevance to us in how we make amines and the problems that we have in making them. But the idea is that, the core idea here is that A, amines are basic, and B, they're pretty good at donating a pair of electrons. So keep that in mind. We're going to need that. How we look at that basicity is the reverse, and that is we look at basicity, which does not have any atom to donate that we can measure concentration, by looking at the pKa of the conjugate base. So we can look at acid easy. We put a pH meter in something, we're measuring the hydronium concentration. If I throw this in water, I don't think it dissolves well in water, but the point is the acid scale we measure. So we basically tend to look at things based on the acid numbers. It's a little easier for us if we can. It's a little easier for us. So we're looking for a good base to have a higher pKa, meaning it's a worse acid. Good base, bad acid, and vice versa in terms of reactivity. Good base, bad conjugate acid, weaker conjugate acid. So what we're noticing here is, in terms of alkyl groups, these are all pretty close. They're not really all that far apart. You'll see a little bit of difference here and there, and we're going to get to that as part of synthesis, but not drastic. None of these numbers are more than 1.5, 2 points apart, not even 2. So remember, tenfold scale, but still 10 times more basic is not really drastic in terms of reactivity. Go back here and compare, okay, this is a 6-point drop. Well, that's 10 to the 6th. Okay, so there's 1,000,000 times difference in acidity here. So 10 times really doesn't add up to much on that scale. For instance, $10 is probably not going to change your life. $1 million might. So again, we worry about big drastic changes, not really small ones. They're still relevant, but much less so. I don't have to worry about gas today if somebody gives me $10. I don't have to worry about paying off anything anytime soon if somebody gives me $1 million. Except for probably jail, because no one's going to legally give me that kind of money. All right. So the difference, though, that we do need to talk about here is the aromatic amines. In the cases on the left, we're talking about anilines. Notice the pKa is relatively low. All right. That means we're getting a relatively good acid out of this. This is the same pKa roughly as acetic acid. So it's coming from something that's really not a good base. This is really not a very good base to generate this strong of an acid. The other side is, these two are a question that I've asked many times. Why do we use pyridine as a base? and not pyrrole. So let's answer it. Why do we do that? Why is this basic and this not? We talked about this in the aromatic chapter 2. And it's very simple. This lone pair is part of the aromaticity. It's resonating around. It's busy. It's not available to be donated to other stuff. So, it's very non-basic. This one, on the other hand, because we have a pi bond to that nitrogen here, is not even in the plane to resonate. So I have this going on as my resonating system. Not drawn very well, but the point is, this orbital is the one that's part of that pi bond. I'm going to leave the others alone, we don't need them. This is that lone pair. It's not anywhere, it's not even capable of being part of the resonating system. It is available 24/7 to go out and pick up an acid. So this is something we use as a base frequently. And that's why, is that its lone pair is always available. And something else like pyrrole, it never is. So we don't have that usability. Okay, so free exam question for you there. All right. Why is the aniline so unbasic? Well, it has to do with delocalizing into the ring. So this is possible. And because it's possible, this going out and picking up an H becomes less likely. It's not impossible, but it's much less likely. So we're talking about, remember, the regular amines were a pKa for their conjugate acids of between 10 and 11. We've dropped off by 6 points here. We're 1,000,000 times less basic. So, yes, technically capable of being a base, very unlikely. Depending on what else is around, very, very, very unlikely. That is coming from something that will never be a base. That's too strong of an acid. So, we can think about that. We'll talk about that more in a later video. Last piece of the puzzle, which is very important for the biochemical context that we're going to deal with after this chapter, the nitrogen in an amide. Very much like pyrrole. It is tied up in resonance. You are not doing anything else with it unless you hit it with a sledgehammer. It is busy. This is the only case of a resonance structure for a neutral compound where adding additional charges in drawing a resonance structure is realistic. Amides actively resonate even in a neutral state, even at room temp, even without anything else around to react with them. This is a big part of understanding why amides are so unreactive, and we talked about that in the carboxylic acids chapter. But it's worth reminding you here because it's going to come back with a vengeance when we talk about biochemistry. Amide resonance is a very important concept, and therefore that nitrogen really isn't available to do anything else with. It's busy resonating back in and out of the carbonyl group. All right, last piece of the property puzzle is this. Under regular pH, basically what's called physiological pH, which is slightly basic compared to water, amines pick up hydrogens. They're more basic than water. So any trace of acid that's around, they're going to take care of it. So we're going to end up with this. We're going to end up with ammonium ions. We're going to end up with quaternary ammonium ions that are protonated at physiological pH. So when we talk about amino acids, when you see them drawn, you'll see them drawn like this, where you'll have an amine that is protonated and a carboxylate that's not. Well, that's why. This gets donated in water. This gets protonated in water. So protonated and then deprotonated in water. And there's an exact pH for that, but again, that's another chapter. My point is, you'll see the protonated version of amines in aqueous solution the first second we start talking about amino acids, and anywhere else you see them, if they're drawn properly, they're drawn protonated. You'll never see that NH2 group here drawn by itself as neutral. It's always drawn as protonated unless you're under extreme acidic, unless you're under extreme basic conditions, which are not physiological ones. All right, we'll stop there. We'll pick up with synthesis in the next video.